In this video lesson, we're going to be covering section 1.2 in our book, Characteristics of Function Graphs. And let's go ahead here. Essential question: what are some of the attributes of a function and how are they related to the function's graph? Functions have different representations. There's analytical, numeric, and there's graphical, and that's what we're going to concentrate on today. Explore identifying attributes of function from its graph. And here we can identify several attributes of function by analyzing its graph. And here in the graph shown, we can see that function's domain in set notation is that x is between 0 and 11. And its range is between -1 and 1, y equals -1. So here, our domain starts here at x equals 0 and continues on to x equals 11. By contrast, the range will start and oscillate back and forth between -1 and 1. And this is similar to the range of a sine or cosine function. Anyway, use the graph to explore the function's other attributes. The values of the function interval x between 1 and 3 are positive or negative. So let's go ahead and examine between x equals 1 and x equals 3. Well, here we have x equals 1. And x equals 3. Now, what are the values? The values represent the output values. And so we're looking for the output. And where do we find the output? We find the output right here. The output values are where, okay, I'm boxing this in, between 1 and 3. I'm boxing in red. So are these output values above the x-axis or below the x-axis? Well, most certainly above the x-axis. And being above the x-axis, those values are positive. Next, the values of the function on the interval from 8 to 9 are positive or negative. Well, here we have x equals 8. Here we have x equals 9. Where do the values reside? Well, they reside right here, where I'm boxed in again on red. Are those values going to be negative, positive, or both? Well, they are negative because our graph is below the x-axis at these input values. So output relative to input. Next, a function is increasing on interval if f of x1 is less than f of x2 when x sub 1 is less than x2 for any x values. And so we're going to just analyze what that is. In analyzing functions, what we do is we analyze looking from left to right on intervals. So we are headed this direction in our evaluation of a function, whether those function values are increasing or decreasing over that interval. Basically, is the function going up, increasing? Is the function going down? Okay, function going up, increasing, function going down like this, decreasing. And we can see we have ups and downs over the entire interval. We talked about interval notation of last section, from x equals 0 all the way to x equals 11. And then, accordingly, function is decreasing if f1 of x is greater than f2 of x when x1 x sub 1 is greater than x2. And so basically, if they're going in opposite directions over the interval. And we will again evaluate from left to right. Okay, C, the given function is increasing slash decreasing on the interval, x equals x between 2 and 4. So here we have x equals 2. Here we have x equals 4. Over that interval between 2 and 4, what is the function doing? Well, the function is just going down all the way. So we will say the given function is decreasing on that interval. Okay? D, the given function is increasing slash decreasing on the interval from 4 to 6. Well, here we have x equals 4 to x equals 6. And over that interval, we are going up. So the function is increasing. So what we say is, just how we could say this interval notation is function is increasing on interval and we're increasing all the way from x equals 4 to x equals 6. So that's going to be an interval notation of what the set notation shows up here. Next, for the 2 points, x1, comma, f of x1, and x2, comma, f of x2 on the graph function, the average rate of change of the function is the ratio of the change in function values, f of x2 minus f of x1, to the change in the x values, x2 minus x1. For a linear function, the rate of change is constant and represents the slope of the function's graph. There is in Algebra 1 something that you learn called the equation for the slope of function. It's going to be m equals y2 minus y1, change in y, minus corresponding change in x. Hope you remember that. What they do in this thing here, instead they replace this with function notation. So instead we call this m equals f of x2 minus f of x1 over x2 minus x1. Okay, that's going to be our average rate of change in this case. Now, the question, what is the given function's average rate of change on the interval from x equals 0 to x equals 2? Well, here we have f of x2, so that's going to be, I'll just put the arrow here, f of x2 minus f of x1. So let's go write this out. Average rate of change, we'll call this the slope over that interval, is going to be f of x2 is 1 minus negative 1 over x2 minus x1. So what we're going to get for that is 1 minus negative 1 is 2. And 2 minus 0 is 2. So our average rate of change is 1. So we'll call this average rate of change over this interval is equal to 1. Okay, next. A function may change from increasing to decreasing or from decreasing to increasing at turning points. Now, in pre-calculus, turning points are going to be called something else also. There are other ways you can say that. The value of f of x at a point where a function changes from increasing to decreasing is a maximum value. So that would be a type of turning point. You have a turning point, one of which is a maximum value. The maximum value occurs at a point that appears higher than all the nearby points on the graph of the function. So a maximum value is going to be right up here. These three that I'm encircling up here are going to be maximums, the very tops. So they would be like peaks. Similarly, the value of fx at a point where a function changes from decreasing to increasing is a minimum value. So your minimum value is going to occur right over here, kind of the valleys. So here are your maximum values right here that I'm outlining, and here are the minimum values down here, circled. Now, at how many points does a given function change from increasing to decreasing? Well, here we are increasing, okay? So, and then we're changing to decreasing, and it looks like that happens here again, second time, it happens here right at x equals 10 the third time. And so 3 points. Okay. Next, what is the function's maximum value at these points? Again, we're talking about 3 points. And we can look over here on our graph, and our function's maximum value here is going to be, okay, maximum value equals 1. And I'm just writing this out here for clarity's sake. Maximum value equal 1. Next, and how many points does a given function change from decreasing to increasing? And then, okay, we are decreasing to increasing here at x equals 4. And we see we're changing from increasing to decreasing again at x equals 8. So it looks like we have 2 turning points here where we're changing. So we say 2. And similarly, what is the function's minimum value at these points? Okay. Minimum values are going to be equal to y equals -1. A zero of a function is a value of x for which f of x equals 0. And so what we're looking for is touching or crossing the x-axis. So on a graph of a function, the zeros are the x-intercepts. How many x-intercepts does the given function's graph have? Well, we count 1 here at x equals 1, another here at x equals 3, and x equals 5, the third one, fourth one, fifth one, sixth one. So it appears that we have 6. And it says identify the zeros of the function. What do we call a zero function? A value of x for which f of x equals 0. So when we list several values, we can do that in what we call set notation. And so we'll say x equals, and we're going to bracket, and this is one thing that set notation is good for. X equals 1, comma, 3, comma, 5. Now it looks like there's a pattern here, doesn't it? Our zeros appear to be 2 units apart. So 7, comma, 9, comma, 11. Roots, solutions, x-intercept zeros related. Okay, I'll just write this down here. Roots, solutions, x-intercepts zeros. I'll just int zeros. And solutions is a slightly different meaning, but these other three are synonymous. Roots, x-intercepts zeros. Okay, let's go on here. Reflect, discussion, identify 3 different intervals that have the same average rate of change and state what the rate of change is. So from here, we can go back and find, well, remember we went over our rate of change, and we found our average rate of change between x equals 0 and x equals 2 of 1. So that's 1. So we'll say interval, we'll do interval notation. What are the 3 different intervals? Well, between 0 to 2 at an average rate of change of 1, and then we're going to have the same, aren't we, between x equals 4 and x equals 6? Four comma 6, and one last interval where we have that same average rate of change between x equals 8 and x equals 10. Okay. Discussion. If a function is increasing an interval from x equals a to b, what can you say about its average rate of change on the interval? Well, remember back here, we had the definition of our average rate of change, f of x2 minus f of x1 over x2 minus x1. Let's go ahead and apply this. This time we're given a and b. So we're going to have f of b minus f of a over b minus a. What can you say about its average rate of change on the interval? Well, what you'd say, that's going to be, that's using the essentially the slope formula to find out what it is. I don't know another way of explaining it here. I'm sure there is. We'll just leave it at that. Okay. Explain one. Sketching a function's graph from a verbal description. By understanding the attribution function, you can sketch a graph from a verbal description. Lyme disease is a bacterial infection transmitted to humans by ticks. When an infested tick bites a human, the probability of transmission is a function of time, since the tick attached itself to the skin. In the first 24 hours, the probability is 0%. During the next 3 24-hour periods, the rate of change in probability is always positive, but is much greater for the middle period than the other 2 periods. After 96 hours, the probability is almost 100%. Sketch a graph of the function for the probability of transmission. And then we identify the axes in the scale. The x-axis will be time in hours and will run from 0 to at least 96. And here we have hours along the x-axis. The y-axis will be the probability of infection as a percent from 0 to 100. And so here we see the graph, the probability shows up on this y-axis. Identify key intervals. The intervals are in increments of 24 hours, 0 to 24 hours, 24 to 48 hours, 48 to 72 hours, 72 to 96 hours, and 96 to 120 hours. Sketch the graph function. Draw a horizontal segment at y equals 0 for the first 24-hour interval. The function increases over the next three 24-hour intervals, with the middle interval having the greatest increase. After 96 hours, the graph is nearly horizontal at 100%. And really, this explains what it is. You have, we are horizontal between x equals 0 and 24. And here we have between 24 and 48 hours, we get a 10, we're going to 10% probability of infection. And from 48 to 72 hours, we have a huge increase from 10% probability all the way up to about 75% probability. So this steepest portion is where our slope is the greatest. Then between 72 and 96 hours, our probability goes up from 75% to, it looks like 90, is that 98% or something like that, very high. And then in the last period evaluated between 96 and 120 hours, probability goes up to that last bit to 100%. So this is the graph, an explanation of it. And next, all right, here we have the incidence of a disease. A rate is the rate at which a disease occurs in a population. Is calculated by dividing the number of new cases of disease in a given time period, typically a year, by the size of the population. To avoid small decimal numbers, the rate is often expressed in terms of a large number of people rather than a single person. For instance, the incidence of measles in the United States in 1974 was about 10 cases per 100,000 people. And here we have from 1974 to 1980, there were drastic fluctuations in incidence of measles in the United States. 1975, there was a slight increase from 1974. And the next 2 years saw a substantial increase in the incidence, which reached a maximum in 1977 of about 26 cases per 100,000 people. From 1977 to 1979, the incidence fell to about 5 cases per 100,000 people. The incidence fell much faster from 1977 to 1978, and from 1978 to 1979, and finally from 1979. So verbally, we have an explanation of what's going on. So it's left to us to fill in the graph. Okay, so we have 1975, there was a slight increase from 1974. The next 2 years saw a substantial increase, which reached a maximum of, in 1977, about 26 cases. So we're talking about years since 1974. So here we have 1974, 75, 76, 77, 78. So 77, we're up to about 26 cases per 100,000 people. So there we have it. That's 1977. From 1977 to 79, the incidence fell to about 5 cases per 100,000 people. So that's 79 is 2 years later. So we had a drastic decrease. The incidence, fell much faster from 1977 to 78 than from 1978 to 79. Finally, and so what it is, we kind of look at this. How do you do that? How do you estimate what they are? We're not given information here, but we know that we fell much faster in this interval between 78 and 77 and 78. And so we could have fallen like to 10 cases, okay, from 26 cases. And then the following year, we just fell 5 more. Now, we're just estimating. That's sort of arbitrary, but we can see that would fit the verbal description. Finally, from 1979 to about 1980, incidents stayed about the same. So we were at 5 in 79, and so we're going to assume for incidences to be about the same, we were also 5 in 1980. Let's go ahead and see if we can reconstruct before 1977. So we're going to call this the peak at 1977. Okay, and let's look at before. 1975, there was a slight increase in incidence. So does it say? Yeah, it says in 1974, which is where we're started, there are about 10 cases. So we're going to say 10 cases here in 1974. And in 1975, there was a slight increase. Okay, so we can say that we increased from 10 to 12 maybe. And it says in the next 2 years saw a substantial increase, which reached a maximum of about 26 cases. So we could say that we went up from, that's 12 maybe, to 20. And then between 1976 and 77, we went up 6 more to reach our maximum. So based on what we were given, these are the values that I came up. Some are exactly as given on the graph. Okay. I'm gonna point to in red the ones they tell us are exactly from the data we're given, and this maximum here. And we know we came down to 5 cases per 100,000 people in 1979. Okay, so that's the same. So some of these are exactly given, and some of these are estimates. Okay, the x-axis will represent time given by years and will run from 0 to 7. The y-axis will represent incidence of measles. I'm going to try to get my writing a little smaller. Incidences of measles measured in cases per 100,000 people will run from 0 to 30. Identify key intervals. The intervals are 1-year increments from, looks like from 0 to 7, right? Okay, the first point on the graph is, it looks like it's 0, 10. The graph slightly rises or falls from x equals 0 to 1, so slightly rises. From x equals 1 to x equals 3, the graph rises or falls to a maximum y value. So we are still increasing the next two years. So the graph rises to a maximum value of 26. The graph rises or falls steeply from x equals 3 to x equals 4. Well, here we have between x equals 3 and x equals 4. That is steeply falling, isn't it? The graph falls steeply from x equals 3 to 4, and then rises or falls less steeply, but we are still falling between 4 and 5. So the graph falls, but falls less steeply from x equals 4 to 5. The graph is horizontal from x equals 5 to x equals 6, is what we see here. Okay. In part B, the graph is horizontal from 1979 to 1980. What can you say about the rate of change for the function on this interval? Okay, let's look at this. We can do this like we did the other one. We can call, remember we talked about f of b and minus f of a over b minus a. Okay, well we can say b is equal to 6. We can say a is equal to 5, and we have f of b is equal to 5, right? Here on the horizontal, that's 5. And f of a is also equal to 5. So I'm going to come over here and do the calculations. So we have f of b minus f of a over b minus a equals 5 minus 5 over, I think b is 6, isn't it? Yeah, b is 6, a is 5, over 6 times 5. So we end up with 0 over 1. So we can say the rate of change is 0. Rate we can say rate of change, which is, it's really the average rate of change, but we're going to use language they have. Rate of change is equal to 0 on that interval. Okay, next. Your turn. A grocery store stocks shelves with 100 cartons of strawberries before the store opens. For the first 3 hours the store is open. The store sells 20 cartons per hour. Over the next 2 hours, no cartons of strawberries are sold. The store then restocks 10 cartons each hour for the next 2 hours. In the final hour the store is open, 30 cartons are sold. Sketch the graph of the function. And so we're talking about cartons of strawberries, time since opening. So I'm going to let you draw your graph based on the verbal data, and then just pause, work it out, and then play ahead to see if you got it right. Go ahead. Okay, here we have a grocery store stocks shelves with 100 cartons of strawberries before the store is open. So we know that right here is this point. In fact, one thing we can do to help our analysis of this is we can create a little table, can't we? So if we say, okay, hours, call this hours, and we'll have this cartons. And at hour equals 0, we have 100. Okay. For the first 3 hours the store is open, the store sells 20 cartons per hour. So we're going to have first 3 hours. So hour 3, by hour 3, we're going to have 100 minus, so it's 20 per hour, and 3 hours, 20. So that's going to be 100 minus 60 equals 40. So we're going to have 40 cartons on the shelves after 3 hours. Okay, next, the store over the next 2 hours, no cartons of strawberries are sold. Okay? And so for the next 2 hours, that's going to get us up to hour 5, right? 3 plus 2, that's the next, that's 5. And we didn't sell anything, but we had 10 cartons restocked each hour. And so we have 40 plus 10 cartons stocked each hour, and we have 2 hours in the interval. So we're going to have 60 cartons. So here we are at hour 5, we have 60. And finally, it says we have and I've kind of got this wrong, don't I, somehow? Okay, the final hour the store is open, there's a reason for it. Okay. I'm kind of revising my interpretation. Okay, what happened is for the next 2 hours, no cartons of strawberries are sold, and it looks like there's no, okay, that's this interval. So we would still have what we had over here, 40. Okay, so we're going to go to 40 right here. Okay, no sold, no carton sold, no restocking, just that's what it is. The store restocks 10 cartons each hour for the next 2 hours. So that would be next 2 hours, you add 2 to that, and it's going to be 40 plus 2 times 10 equals 60. And so here we have, over these next 2 hours, that is our restocking. And then in the final hour, the store's open, 30 cartons are sold. So we have between hour 7 and hour 8, we're going to have 60 minus 30 cartons equals 30. So here we are, we've sold. So this is really the profile of the amount of strawberries on shelves in the store over these intervals. Yes, if we examine the details between these hour opening and hour 3, we're going to see a lot more detail on the graphs, some places, but based on the data we are given from the text, this is the best representation graphically we can derive. Explain 2, modeling with linear function. Okay, so now we're talking about something called a linear regression. And using a graph and calculator, we can make a linear regression with a correlation coefficient. Okay, and that correlation coefficient R can be between -1 and 1. And so we can talk about that. We can use a linear model to make predictions and decisions based on data. Making prediction within the domain of a linear model is called an interpolation. Making a prediction outside the domain is called an extrapolation. So usually your interpolation is going to be more realistic since it's within the bounds of the data than an extrapolation, which requires an extension outside. Okay, perform a linear regression for the given situation and make predictions. What I'm going to do for this is not proceed further at this point in the lesson, and I'm going to get another video that actually goes over the using the calculator for this. So we'll just stop at this point. As always, good luck and thanks for viewing.